So maybe that all makes sense. So hope you get some good numbers when you do this. Like I said, obviously this is new to me too. I'm walking around helping students. If there's a number, we redo it. But here we're not really redoing it, and we wouldn't know to redo it unless we did some calculations. But that's for you to do, so I don't want to do that and check the numbers. Although maybe I'll check it later. Okay, so coming back here, let's do our last of our 5 experiments, or 5 runs before we move into part 2. And so I'll just go ahead and grab this and make sure to step back a little bit and say ready, go, and stop. Yeah, it definitely popped off there. And good, fell to the safe side. Got caught there. And again, good number here. That thing was zipping. And so this went at 1.82 seconds. All right, so as I had already mentioned a few times, and say it again, you can write those down and do calculations either now or wait till we do part 2. But now that you have height and time, get out your calculator and get this row right here, which is the acceleration. And I'll come back to tell you how to make the graphs here in just a second. Let's jump over then to part 2. And part 2 is dramatically different sets of weights. Let me just, what's the best way to do this? Why don't I just put the lighter one right there. And note that the heavier one is a 270. And point out that the hanger itself again is 100. So 100 and 100 make 200. Then a 50. And then a 20. Let me confirm the 20. That looked kind of big, but that's it. Oh, I guess it's made out of aluminum, so a little fatter than our steel ones. All right, so this is the heavy one. This is the 270. And then let me make this the lighter one. So this will be 250. And remember, the hanger itself is already 100. So that's 200. And then I'll just put a 50 on here. All right. And so as we mentioned earlier, the difference between these is 20. And that will remain for the next 5 that we do for part 2, because we want the net force to always be the same number, which is the difference between them, which will be the 20. Okay. So let me just double check. That looks like a 250. That looks like a 270. Good. And if I then take the lighter one all the way down and put a little weight on it so it stays there, I can then measure the starting height for part 2. And my guess is with a lot less tension than we had, this probably doesn't bend as much, and so the height's probably a little bit higher. And sure enough, it has gone back up to 146.4. And so I'll write that down. Oh, I didn't give my place, so write it. But 146.4. And I'll just say, here is my height in meters, and now I'm going to get time in seconds. 1, 2, 3, 4, 5. And I'm going to use this equation to then calculate the acceleration. Okay? Okay, so there's the height. Now let's get the time. How much time does it take? All right, put the watch over here. Let me reset it and let it begin. It's tilted inward, but I don't think these go very fast, so I don't think any of these will fall off. And so I'll go ahead and say 1, 2, 3, go. And I'll just watch it, boom. And that's the fastest of these 5. So that's a 3:02. Oh, I left the marker over here. And so 3.02 for that one. And then we put 200 on each side. So the 250 here now becomes a 450. Oh, it did come off a little bit. Or was my hand doing that? And the 270 now becomes 470. And if I put I'm going to wait there for a second. We'll probably stretch the string and tilt the pole just a little bit. What were we at? 46.4 last time? Yeah, because we are at 145.5. And so I'll write that down. And so 145.5. And let's get the time then. Okay. And so clear that. And come over here. And 1, 2, 3, go. And you can even see the more mass, less acceleration already. And I got a time of 4:03 seconds. And let's go to the third one on here. And we'll need to increase by 200 on each side. Just grab a couple of 200s. And give myself a little bit of room here. Slide that on. Okay. So that's what, 670. And put the 200 on here. So that's 650. And bring it down to see what our new height is. It's going to be a little bit smaller as this changes the weight a little bit. And I'm going to, I think twisting it like that before gave it a little extra friction, but I wanted it to fall inward. So hopefully it didn't change our data too much. But now that it's going so slow, I'm going to try to get it straight up and down. I don't think it's going to bounce off and hit me at all. And so sure enough, 144.0. All right, so my height is 100 and, well, let me double check that. 44.0, that's 1.5 centimeters. That's a little more than we've been seeing. And I want to just kind of confirm that. Yep, 144.0, okay. Take that for what it's worth. All right, and now let's get the new time here. All right, so that's off. And on the count of 3, 1, 2, 3, go. And then really slow. And I get a time of 4.66. All right, so 2 more times. Let's add 200 again. I'll grab 2 200s here. And so we'll flip this over here and slide on a 200 here, which I guess is going to make that heavier and go down. And then this, we'll put another 200 here. Does that make us 870 over here? And 850 on the lighter side. And then hold it into position with this little weight. And we'll have a new and lesser height. Yeah, there's getting to be a lot of tension on here. This is real heavy. Okay, so we're at 142.6. And I know, yeah, 142.6. I'm always amazed every time I do this, how much that string really stretches under the tension. So 142.6 keeps getting less and less in the vertical height because that string just keeps getting longer and longer under all this tension. Okay, and so getting ready to start again. 1, 2, 3, go. It's really slow, lots of mass, really sluggish, and stop. And so I get 5.48 seconds. Okay. And one last time here. And so I will grab 2 more 200s and put, let's see, 2, 4, 6, 8. Yeah, so we are at 1050 here, which means I guess we're at 1070 on this one. And wow, yeah, lots of tension. I can just feel the tension and the weight in the string here. All right. And so, a little bit of weight to hold it one last time into place. There we go. And it's going to be fun to see how short the string is now. Yeah, wow. 141. Yeah, 141.3. And so over here at 141.3 centimeters, which is 1.413 meters. And the last one, which, by the way, when you do the graphs, this one does have a tendency to be off. I would say when I'm face-to-face, a third to a half of the class, this one always just looks weird. I think it's the friction in here in the bearings. In fact, there's so much tension, it's already pulling it over, so maybe I better go quickly here and say, all right, let her go. And so 1, 2, 3, go. And I think there's a lot of friction and bending. Oh, good. And it stayed up, but it is really twisting. Okay. And so I got a time of 6.66 seconds. All right. And so there's your raw data. Now let me take a couple more things or talk about a few more things before I wrap up my end of it. That is you and I collecting data together and you start analyzing the data and start answering these questions. The first is, and I've already said this a few times, but your job next is to get out your calculator, use this, and to fill in the acceleration, and then also over here, Same formula, put in the height and the time, and get your accelerations. And once you have that, of course, you're done with your raw data, so you'll be done with your page 19. But then page 21 has a graph that says plot net force on the x-axis, so that's your independent variable, and your acceleration on the vertical axis. Okay, and so go ahead and do that. I'll talk more about this, but they also say the same thing on the next page, which I think is what, page 22, is to go ahead and plot the mass on the x-axis and the acceleration on the vertical axis. So there's your independent and there's your dependent. Now, back to part one. When you do this, hopefully what you will see is 5 pieces of data that look pretty straight and maybe go close to the origin, maybe not exactly at the origin, because you are trying to prove, let me come back to here because this is going to be part of your discussion questions. Remember, we're trying to prove if this equation is valid. And remember, we did not use this equation at all to get the acceleration. But had we used this equation says they're proportional. This equation says we would have gotten a line that would go through the origin. Let me just remind you, the equation for a line is y equals to mx plus b. And so when something is proportional, what that means here, or what this would mean, is the b would be a 0, and the proportionality constant would be 1 over the mass. And don't confuse this m, which is slope, with that m, which is mass. And so your proof is right here. It's easy to miss it if you're not paying close attention. And this is usually when I walk around in a face-to-face setting and I say, hey, look at your graph. What does a straight line tell you? And I would say probably half the class has kind of forgotten the words of proportionality. I said, to prove something is proportion, it should be a straight line through the origin. And I would say that your data has something very close to a straight line and very close to the origin. The fact that it's very close probably just tells me that there were some errors made by the people collecting, ooh, he's going to fall, collecting the data. Oh, just in time. Okay, tells me that there is really some imperfections on people collecting the data, maybe people doing the plot, maybe some friction in the bearings, so the bearings weren't good. But I would say this is your proof. And so this is all you have to do for part one. This is your proof to say that at least half of Newton's second law is correct. This straight line here is proving that acceleration is proportional to net force. Which is then why part two, when you do this graph, you will hopefully see something that looks more like, and if I can use a fancy word from your algebra class, a hyperbola. See, a hyperbola is the shape of y equals to something over x. I'll just say 1 over x. And this hyperbola would prove it is inversely proportional. However, your author doesn't stop there because 2 reasons. One, how do you show for sure this is a hyperbola versus a piece of something else like a parabola or an ellipse? Very, very difficult. And so instead of that, we have a better answer. I'll explain it in a second. But the other reason here is I have a feeling that a lot of you might be a little bit weak in the difference between a hyperbola, parabola, and ellipse. And so your author doesn't want to focus too much on whether that's a hyperbola or whether that's an ellipse. Because there is an easy way to do this problem. And it sounds kind of weird at first, but that's why I wanted to explain it your author says make yet another graph. So notice we're making 2 graphs for part 2 and only 1 graph over here for part 1. Because by the time we did part 1, we only needed 1 graph to prove it's proportional. Straight lines are easy to work with. Hyperbolas are not. And so that's why after you get this first graph, instead of trying to prove that this is a hyperbola, which would prove it's inversely proportional, we will just do this. Let's plot on the horizontal axis, not mass, but the inverse of mass. 1 over the mass. Now here's some good news. You don't have to make a new column that is 1 over the mass, because the author already did. Let me hold up page 19 again. On the very far end, these numbers over here are the author's calculations of 1 over mass. Couldn't hurt to confirm it and get out your calculator here, but that's what we want to plot on the horizontal axis. And then on the vertical axis, we still want to plot acceleration, because I'm hoping what you will see is something that is nearly a straight line and nearly through the origin. Because again, I'll ask it like I did back here in part 1. If you get something that is a straight line and goes through the origin, what do you call that? Proportional. All right, so watch this. If I see something that is a straight line through the origin, or at least near it, because near it just means it was supposed to go through and the imperfections of us humans making the measurements. But here's what this would say. This would say acceleration is proportional to the inverse of mass. And if you rephrase that, that is the same as saying acceleration is inversely proportional to mass. So since straight lines are so much easier to work with and so much easier to prove, instead of trying to do a hard shape to our curve, we'll do an easy shape but a hard axis. That makes sense? We'll change an easy axis, hard curve to easy curve, hard axis. And that's a little better one. So I would say shoot for straight lines. Straight lines show us that proportional. So this is saying acceleration is proportional to the inverse of mass, which is another way of saying it's inversely proportional. Let me jump all the way back over here to the equation, and I would say we have now finally proved both parts of Newton's second law. We have proved that the acceleration is directly proportional to net force. That was part 1. And now we have proved that it is also inversely proportional to the mass. And so hopefully all that discussion will not only help you as you begin to do your 3 graphs, but it'll also help as you begin to answer these questions. And you'll begin to see why, like in the first one, the author says, what is the shape of your force versus acceleration? They want you to say, it is a straight line through the origin, and therefore, question 2, you can say they are proportional. And he goes on to talk about those, but I want to just add that the last 2 questions probably need some clarification. The second to last one right here, it says, why was it necessary to plot the inverse of the mass? And I think that's an overstatement on his part. I wouldn't say it was necessary as much as I would say it was easier and better. I'll say it again. Watch. Come over here. To show that these 2 are inversely proportional just requires me to show this is a hyperbola. It is not necessary to go to this graph. Now, it is better and easier to go to this graph, but not necessary. I just have to know how to show something's a hyperbola, which, at your point in your education, I don't know if you know how to show that. And so his question is really not, is it necessary, as much as, why was it better? And I would just say, because showing something is proportional is really easy. Showing anything else is actually pretty hard. So you're better off to show something like this. Acceleration is proportional to its inverse than trying to show this is a hyperbola. Now, the last question is also a great question, but it could be written a lot better. Let's see if I can find a place to put it. Let me come back over here. This might be a good place to put it, because here's what your author is saying. Let me do a little abbreviation here, but he says in this problem, and it's got 3 parts to it. He says if the, and let me just put A for acceleration. So if the acceleration is constant, he should put then force is, and he just left it alone, but he wants you to put proportional or inversely proportional to the one that's missing. And so we have A here, we have force here, and so this should be mass here. And he does all 3 combinations. The next one says if the mass is constant, then force is blank to, and which one is missing? Acceleration. And I think it would help if you put a blank and say to mass, to acceleration. So they want to know how force is related to mass. They want to know how force is related to acceleration under these conditions, because they change under the different conditions. And then finally the last one is if the force is constant, acceleration is blank to mass. And so again, all of these should have either the word proportional or inversely proportional. So how are the other 2 related if one of them is held constant? And I'll help you in doing this. You will hopefully see it in the math. Come up here, now that you've confirmed that this equation is true, imagine holding A constant, how are these 2 related? Or imagine holding M constant, how are these 2 related? Or this one here, holding force constant, how are these 2 related? And I would say the experiment that we just did, in part 1, we held the mass constant. So we've already answered that. And in part 2, we held the force constant. So we already answered that. We did not do a problem where the acceleration was held constant. But hopefully you can also see what would happen between the relationship of force and mass if that was true also. So again, I think that last question is a really good question, but it's poorly laid out and the students don't quite get the point of it. And so I like to explain that, even in face-to-face, but even more so now that we're on a remote learning. Okay, so I'm going to leave the rest to you, and if you have any questions, shoot it off to me. Good luck with the lab.